So hi everyone. Last meeting, we have discussed about virtual memory. And virtual memory allows processes to have an address space that exceeds the physical memory available. So we have discussed, right, that the main memory is limited. So that's why we use the virtual memory instead. The virtual memory makes use of the secondary memory as well as the main memory to give us the illusion that we have a larger or unlimitedness space. Anyway, our topic for today is paging. And paging is a technique in virtual memory. And it permits the physical na address space of a process to be non-contiguous, have or giving us an efficient na utilization of memory resources. So you will see later what I mean by this. And paging is also a fixed size partitioning scheme. So the secondary memory and the main memory will be divided into equal fixed size na partitions. So don't worry, you will understand this in the next slide. So assuming that we have a really large na program, and what I meant earlier by contiguous is that we need to load this program into the main memory to execute it. So that means that we are going to look for a large na available contiguous space into the main memory to fit this program. But that's not the case. That would be difficult to do. So what if there is no large na hole available to fit this program? So what we do is divide this large na program into smaller na pages. So this page one, let's say, contains the first set of data and instructions. Then page two consists of the next set of data and instructions, and so on. Okay, and what we are going to do is load these pages into the main memory. So let's say this page two is loaded into this part of the main memory. And then this page one is loaded into this part of the main memory. So as you can see, in in the virtual memory, we have the pages. Okay, but in the main memory, we have the frames. And those pages, or let's say uh, pages that contain less frequently accessed na data and instructions by the CPU may be loaded into the secondary memory. Or let's say assume natin na we no longer have space into the main memory. So what we do is to load this page 3 into the secondary memory for the meantime. Okay, so pages of a process are brought into the main memory only when there is a requirement. Otherwise, they reside in the secondary storage. And we must take note that the size of the page is the same with the size of the frame. Okay, so we have mentioned earlier, if we go back to the previous slide, that in the paging technique, the secondary memory and the main memory are divided into equal fixed size na partitions. So that's why we have this mechanism, or that we have this restriction that the size of the page is the same with the size of the frame. Okay, now one page of a process is mainly stored in one of the frames of the memory. So like this, page 1 is stored in frame 1, page 2 is stored in frame 0. So the pages are not stored at the same location, rather at different locations in the memory. That's why we call it as non-contiguous. Okay, so now how do we implement this exactly? So what we need is a logical address and a physical address. So the logical address is being generated by the CPU, and it contains the page and the offset. So the page is the address of the page, and the offset is some mechanism for us to iterate through the contents of this page. Okay, and we also need a physical address to access this main memory. So the physical address is the actual location of the data or instruction that is stored in the main memory. And the physical address is contains the frame, the address, and the offset. Okay, and one thing that we must take note is that the offset offset in the logical address and the offset in the physical address are the same. So our problem now is how to map this page with a frame. Okay, so we know that this page 2 is mapped to frame 0. This page 1 is mapped to frame 1, but how exactly? Okay, so let us see. So what we need is a page table that creates the mapping for us. So we list down here all the pages. So let's say you page 1, 2, and then 3, and then the frames and the frames that they are mapped to. So we know that this page 1 is stored in frame 1, right? So page 2 is stored in frame 0. And then the page 3 is invalid, so it is not stored in the main memory yet. Okay, so the page here is mapped with a frame. So let's say that we want to find page 2 from the main memory. How can we do that? So again, we make use of the uh, page of the logical address. Okay, so we see here a simplified na form, but we basically point to the address of page 2. Okay, so this is page 2, and then it is stored in frame 0. Okay, and then now, how can we iterate through the lines of codes? So for line 1, or for the first na line, so the offset will be 0. So we must take note that the offset is what we add to the base na address. So we can iterate. So this would be the address of page 2 plus 0. That would be this line 4. Page 2 address of base address of page 2 plus 1. That would give us the address of line 5. Then base address of page 2 plus 2, that will give us the address of line 6. Okay, so here, second line, that will give us an offset of 1. Third line, give us an offset of 2. And then fourth line, that would give us an offset of 3. Okay, now, any idea about the size of the virtual address? So actually, the size of a virtual address depends on the architecture and the operating systems used. So in most modern operating systems, the size of a virtual address is determined by the number of bits used to represent it. The common sizes include 32 bits and 64 bits. Okay, so this has been the simplified addresses to keep our explanation simple. But in reality, we have 32-bit na address for logical na addresses. So suppose that we have this page number. This is the addresses of the pages. This contains the addresses. And then we have a page table that maps the address of the page and the frame na address. Okay, so this one, let's say the page number, say page 1 is mapped to frame 1, right? Which has an address of 0x0004 and so on and so forth. Okay, so this page is divided in, this page is 20-bit, and the offset, on the other hand, contains 12 bits. So we have a 32-bit na address for logical na addresses. Okay, so anyway, in the next page, we are going to discuss about multi-paging.